Yeah, hey everyone on Zoom. Today we'll be uh, me and Carlos will be starting a new series on graph machine learning. And instead of going to, let's say, like advanced topics like graph neural networks or anything, in today's tutorial we will be looking at basic graph theory, like what are graphs, how can you use them, and what's like the classical graph theory it looks like. And for that, I'll post the, yeah, and similar to all the tutorials, we again have a Jupyter notebook on Colab, which you can run. And so I'll post that into the chat. Um, so the link I posted is the link for the GitHub repo for this series. And if you open the link, I can start sharing. Wait, share. Okay, so yeah, that's the repo. And to go to the repo, click on the first notebook for this lecture, or I will post that into the chat again. Yeah, once you have the link, you can open it. I think I opened it already. Yeah, and then click here on open in Colab. So this will redirect us to Colab. And since this just it's basic graph theory lecture, we don't really need any GPUs. So you don't really need to do anything. You just have your CPU as the hardware accelerator and do a connect here. Okay, and people on Zoom, please let me know if you have reached to this stage so that we can start the lecture. A thumbs up would be nice. Thank you. Okay, we'll get started. So first part is like why we are talking about graph machine learning. Because one of the main reason is that, like, if you want to know basic machine learning, you start with, let's say, tabular data, or then you move to images, and then to sequences, let's say time series or language. Then probably you would move to, let's say, some more complex kind of data set, let's say audio. But there is a different kind of data sets in real world, which are like social networks or biological networks, and uh, they need a different kind of formulation based on graphs. And that's why graph machine learning is an area where we have set of techniques and algorithms to leverage the graph structural information for the tasks. And since in the graphs there are nodes and links and kind of all of your in each of there are relationships between the different part interactions inside your data set. So that's why graph is or graphs are a natural way to represent those relationships. And graph machine learning uh, for the supervised task can be uh, broken down into three parts. The first one is node classification. I can just make it bigger, one sec. Yes. Yeah. So first one is node classification. For example, Twitter is a good example for node classification, that if you have a person using Twitter, and based on their followers and who other people are following that person, and based on their tweets, you might be able to predict what kind of their political affiliation is. Yeah, another task could be link prediction, that given some users and products, where some users prefer to buy some products and some specific products are popular for some users, then you can have potential purchases, or kind of learner representation between users and products to make a recommender system to pitch them new products based on their purchases. And based on graphs, one common example is chemical compound analysis. For example, it's very popular in chemistry or in drug discovery, that if you have a graph given the molecular structure, you can model these as all the atoms could be the nodes and all the bonds as as the edges. So, and that's why you can model them. Uh, yeah, you can model those graphs or the chemical compounds as graphs, and then that becomes your graph classification task, that based on the properties of those nodes and edges, you want to predict the compound properties, whether they are toxic or non-toxic. And before starting with graph machine learning, why it's important to understand some basic graph theory, because uh, basic graph theory, I would say it comes from theoretical computer science. People have been using it for like past 60 years, and most of the graph machine learning methods have their mathematical foundations in graph theory, based on their nodes, edges, and connectivity. And that's why it's important to understand how graphs look like and how they work. And in tutorial 2, we'll look at one such problem where we would like to represent nodes in a graph as numerical vectors, and that's where some of the classical graph algorithm, let's say like breadth first search or depth first search, will use, or graph traversal algorithm. So that's why there is a huge algorithmic basis behind those algorithms. So let's get started. Okay, so if I have to define a graph, it's just a collection of vertices, which are nodes, and edges, which are links. And so here you can see this like a graph which has 6 nodes, and there are some connections between the nodes. And these nodes and edges, so it's the other name is vertices, which is like the fundamental unit of one graph, and it could be labeled or unlabeled. Then the edges are links which connect these graphs. So for example, in this image, all the numbers with this circle represent each node, and we have edges connecting each node. And then we could have like a loop, which is the self edge, which a node connecting to itself. And then we can also define a cycle where we have a path. If we follow and we will encounter the same nodes again and again. So that's an example of a common graph. Okay, next, going on with the types of graphs, we can have an undirected graph. So everything, so let's say here are 7 city names and they are connected to each other, and there is no direction. So what you can assume is that this is like bidirectional, that for example, you want to go from this city Blacksall to Dunwich, then either you can go from Blacksall to Dunwich or the other way around. And so there is a bidirectional information uh, flow between these 2 nodes. Another example is a directed graph, where you have specific information flow or connectivity between specific directions of cities. For example, here there's a link going from this city Harwich to Blacksall, but there is no incoming arrow. This means that if consider if this was like a road network, and you can assume that like it's only a one-way connectivity. So that would be an example of a directed graph. Okay, next example is of a weighted graph, where you have nodes and the links, but each node or each link has some weight associated with it. This could be like, for example, distances, or you can say like road distances or time taken for moving from one city to another. Uh, or this could be like some cost. Let's say you want to move from Blacksall to Dunwich, then it would cost you like 15 units. So some kind of so it's basically like a numerical quantity you can associate it with each link. Okay, next is your here you have like an unweighted graph, which is like similar to what we have here as an undirected graph, that there are links, but you can assume that the each of those links has the same weight. Okay, and then you can have a multi-graph, so which can mean there are multiple edges between the same nodes, and it can be directed or undirected. So for example, let's say there are 2 kind of road or rail. So for example, let's say you want to go from Tucson to Phoenix, then you have different kinds of modes available. Either you can drive or fly. So that would be like an example of a multi graph. Okay. Coming to the representations of how do you represent graph, you can have an adjacency matrix, which is just like a 2D matrix wherever there is, and then you initialize it starting with 0, and then wherever you have a connection, you put it 1. And since there are no self edges, you will put the diagonal as 0 here. So for example, the node 0 connects to 1 and 2. So each node here in the rows will have value 1 for corresponding connections with node 1 and 2, and so on and so forth. Okay, then another representation is an adjacency list, that you have this graph with 4 nodes and 5 links, and then you can have an adjacency matrix representation, or you can have an adjacency list that you take a node and then just put all of its connections in one list. Okay, and that's all theory right now for getting started with this lecture I have. And for all demonstration purposes, we will be using the NetworkX library. So you can just get started by clicking on each cell, and then we will go through each of the examples. Okay. Okay, so before we go to the code part, does anyone have any questions related to any graph concepts? Yeah, so if you're good, just give me a thumbs up and then we'll move forward. Okay, thank you. Okay, so moving on to undirected graph, we have seen like enough theory above. Now it's time to like implement some stuff. So right now, NetworkX, we are using NetworkX and this command nx.graph with nothing going in between. That's how you initialize an empty graph, but then you define an edge list saying that there are edges between. So you can have an edge list, or first define all the nodes and then say what edges are there, but NetworkX also works with just mentioning the edge list, and it will automatically find out the number of nodes inside. So there are 6 edges between these 7 nodes here. And once we run this edge list, and then we call this function from NetworkX on this graph G, which says, okay, add edges from the edge list. And once we run this, and now we would like to plot it or see how the graph looks. So for that, first we need to provide each node its XY coordinate if you have to plot it. And for that, we are using a spring layout. So in NetworkX, there are multiple layouts. Like for example, if I run this, let's see what happens. So we have this nice looking graph with like six edges and 7 nodes. But like for example, if I have to put like shell here, so instead of the spring layout, because in spring layout, all of your nodes are like spread out with some distance so that they are not overlapping with each other. So what we can do here is use this shell layout to see like what difference it makes. So it's the same graph, but now the order and the links have changed here. So there are multiple ways to plot such graphs, but we'll be using Spring, or there's a force director algorithm. We'll talk about it later, so that we can use to plot your graph. Yeah, again, you can have like random layouts for the same graphs here. For example, this you can have a random layout to plot, and it's different than what we had earlier. But I would say it's good to use Spring, or there's another algorithm which we'll discuss. It's good to plot your graph so that all of your links and nodes are spread out and looks good, looks nicely. Okay, now we'll have a directed graph. So for the difference is that when we initialize our graph, we were using nx.graph, which is responsible for having an undirected graph. Or having a directed graph, we'll have this nx.digraph function, and we will initialize it, but we'll use the same edge list. Now the difference is that it converts this edge list to a source and a target formulation. So the first entry becomes your source, and your second entry becomes your target, and then we'll see a directed edge between starting with the first entries and ending at the second entries. Okay, okay. And similarly, we plotted. Now you can see that our, Yeah, so once we plotted, you can see each of our edge starts with A, like it starts with A, goes to B, and then so on and so forth, following the edge list. And we can verify if it's true or not. So the first element is like from an edge going from A to B. So now we can see in our graph we have an edge going from A to B, and then you can just verify that it's the correct graph. Now coming to weighted graphs, we have the same formulation. It's just that we have this key weight associated with each node and its corresponding weight. So, and we have weighted edge list. We can either have a directed or undirected graph. Both are fine here. Okay, once we run this and see, try to print edge labels. And again, we use the string layout. Since we have already defined this position of the graph in the first part, we can use the same positions because our graph is still the same. It's just that the way it looks is different. And now we can see that, okay, the edge, weighted edges we defined, let's say for A to B has some weight 10. So then we can verify if there is an edge in the graph going from A to B with weight 10. Okay, next we can look at connectivity between graphs. So right now we have this graph G1 and G2 and some edges. And once we run this, and connectivity is an important aspect of graph where we would like to know if there
Yeah,
is,
Dub, do
hello?
you, do you, do you allow questions as you're speaking?
Yeah, sure.
Okay. Um, a quick question on the weighted graphs.
Yes.
Is that just the labels? The numbers that's shown are just labels, or they're actually numbers that you can compute with?
I mean, I'm not getting a question. So because we already,
Textual labels. I mean, you put them
yes.
in something that looks like JSON, but are they text labels or are they
No,
actually
these are
numbers?
numbers.
Yeah.
Yeah,
Okay, so
because
The,
I don't have a string
so
literal here. So if it were a
right.
string, then
Okay.
I'll just put like a string here, but these are numbers.
Okay, fine. So
Yeah.
so you can put anything attached there
Yes.
in this kind of graph, text or
Yes.
numbers or
Yeah.
something else.
Yeah, I
Okay,
think it
thank you.
depends on what task you want to do. Let's say if I put
Yeah,
string, then I won't be
yeah,
able to do like graph traversals or like
sure, sure.
running like a shortest path.
Yeah,
So
yeah.
yeah, then you need numbers here.
Okay, thank you.
Okay. Moving on, coming back to our connectivities, we can have like some edges going here and there. So even before we talked about connectivity, we can just, one way is to just like plot it and see if they are connected or not. But let's say you have a bigger graph and by just mere visualization, it might not be true. So let's first plot graph G1 and we can see that, oh, there are, in this big graph, there are two subgraphs, but they are disconnected with each other because the way we have defined is that node 1 and 2 and 3 connect with each other, and then there is a separate uh, subgraph of nodes 4 and 5. But in the next graph in G2, we have defined 1, 2, 2, 3, and 3, 1 connected, but we also connect node 1 and node 4, and then we can plot it. So that's like one way to find out, but NetworkX provides you a function is connected and which can tell you. And basically what it's doing is it's running some graph traversal algorithms in its function and which tracks if you can reach all of the nodes starting from some position. And if you can, then the graph is connected. If not, then you'll say, okay, the graph is not connected. Okay, coming to graph concepts, here we will look at some node measures. Uh, and the meaning with node measures is that given the connectivity of graph, which nodes are important with or in the graph, because like for example, consider like a map where there's like cities and there could be like major hubs of transport where the most of the traffic passes by. So that could be like one example of the importance of those nodes. Okay, so for illustrating this example, we can have this graph here where I have like different number of nodes and different edges connecting to it. Okay, and the other layout I was talking about is this Kamada-Kawai layout, which is a force-directed algorithm. What it means that it tries to spreads out the nodes and edges as possible, that they don't overlap with each other, so that you can look the graph very nicely. Okay, and one measure of importance of the nodes could be the degree, that if many of the edges connect to that node, then it's possible to say, okay, that node is important. Let's say, for example, if you want to move from from node H to node C, so there are multiple ways, but the shortest way could be from going from H to A to C. Consider this is like a equally weighted graph, but if node A was not there in this graph, then you have to go either from H to G, E, D, and C, so take a longer route. So this might tell that since A is like a spoke, or like lots of connections are coming or going out of this node A, it might tell you the importance of this node. So a normal way to say about the node is just the degree, that how many and other nodes are connected to it, and we can have this function, this degree, which will tell us that, okay, what's the degree of each node, and then we can iterate over it to see what's the degree of each node. Okay. Next, we will have a directed graph, similar example, where here also we would like to know the degree, but in directed graph, this concept changes just slightly, that now you have this concept of in degree and out degree based on how many links are going out of the node versus how many links are coming inside of the node. So for example, if we see this example of node A, there are 4 links or 4 edges going out of node A and 1 edge coming in. So we can say that, okay, the in degree for this node A is 1 and out degree is 4. And again, we also have the same function for directed graphs. It's called in degree and out degree, provided by this NX library. And once we run this, we should be able to plot all the in degrees and out degrees here. Okay, and now we'll look at some graph level measures instead of the node degrees. So to illustrate the graph measures, we will look at this Zachary Karate Club graph, which is a very which is a very famous example of a graph we would find in many books and other tutorials. And in this graph, each of the vertices and nodes represent the members of Karate Club, of Zachary's Karate Club. There are total 34 members. And how this guy built the graph is that he looked at the connections which the members made out of the club, whether if the people are socializing together or going out together. So, and then he made this graph by making some links. And this graph can be called from the NX library by just using this Karate Club graph function. And now we'll use the same Spring directed algorithm to plot this, which will plot those nodes nicely, so that we can look at each of the nodes. Okay, how plotting works is that first you have to we have looked at similar example. This one is more detailed, that yeah, you can put the graph inside the draw function. You want the labels to be shown, and these are string labels. Now you will choose the font color, which is white here in hex, and then you'll say how big your node should look like, what should be the node color, and the most important thing is what should be the positions, and these positions are the output of the Spring layout function. Okay, and once we run this, we should be able to see the Karate Club graph here. So yeah, so this is Zachary's Karate Club graph. There are 34 nodes, there are some connections, and just based on observations, we can see that, okay, like node 0 and node 33 or node 32 looks important, but we can also have the centrality measures, which we're going to discuss now, based on that what nodes are important within the graph. And there are several kinds of centrality measures. We'll look at 5 of them here. So the first one is degree centrality, which tells us that what fraction of total nodes one node is connected to. Okay. And the next one is closeness. It's the average length of shortest path from this node to other nodes. So let's say, for example, you start with node 0 and then you do like run a shortest path algorithm from this node to remaining 33 nodes and then see what's the average path length. And there are other centrality measures such as betweenness, eigenvector, and page rank. So I'll look at each one of them, and for this network, it just provides functions to calculate each one of them. So in this code, yeah, we are calculating all the 5 and then plotting them, and based on the values, we'll see that. So for all the 34 nodes, let's go back to degree, and we'll see that, okay, for node 0 and node 33, these one are the highest nodes with the highest degree centrality, which we also observed, but this our observation is now backed by some math behind that. We are able to see a higher degree centrality for nodes 0 and 33 here. Yeah, same thing goes for the closeness centrality for, again, node 0, but here we see that this node 2 is also appearing with a very high closeness centrality. And why is that? Because node 2 is also like it's between the center of the graph, so that it can reach the other nodes pretty quickly instead of, let's say, node 26, which is very far away. So these measures are kind of tells us that there are different, you can assign different importances with each node for this graph. Okay, and now covering the betweenness centrality, that of all the shortest path between pairs of nodes. So for example, let's say you want to go from one node to every other node, which means that it would be, let's say, like uh, n plus 1 by 2 or n minus 1 by 2, something like that. So uh, out of all those shortest paths going from between all these 34 nodes, in how many of those shortest path you encounter one particular node? Here we see that for betweenness, we still have node 0 and node 33, because because we can see that for these are like the central nodes for these two subgraph. I won't say subgraphs, but we can also see that there are like two communities in the karate club graphs, and for one community, which is like the bigger one on the top, they connect to the node 0, and the lower one is uh, connected to node 33. We'll look at the connectivity in the graphs in the next exercise. Okay, and next, going to eigenvector centrality, which means that and how this node is connected to other important nodes. And here also you'll see, we see that, okay, node 0 and node 33 have a very high value, but we also see that node 32 is also shown to be important in node 2, because 32 is like very closely located to 33, and it also connects to many other nodes, which is an indication that this node is also connected to many other important nodes, and that's why it's showing up with a high value in eigenvector centrality. Okay, yeah, so next part is connected components, that and it's similar to the is connected function, which we looked in the previous examples. Now we can run this connected component just to find out, okay, how many connected components in one graph is there. So right now in our Zachary Karate Club graph, we don't have a disjoint set of nodes which are just like lying somewhere else and it's not connected to the whole graph. At least, and each of the node at least have one or two connections uh, in with other nodes. So if we run this is connected function, or the connected components function, we find that, okay, the algorithm tells us that, okay, the graph has only one connected component. Okay, before we move to community detection, does anyone have any questions? Okay, we'll move on to
question. Can you go
what?
back to the results?
Yeah, this one.
Yeah. Is there,
Yes.
I have the impression that some of the columns should add to one, like probably betweenness. Is there any condition on the numbers?
I'm not really sure because I think for degree it just says that what's the fraction. So if like there are like 34 nodes, and if node 0 is connected to, let's say, like
Yeah.
16 or
Okay.
17 of them, so then it will say, okay, I am connected to like 48% of all the nodes in the graph. But I'm not sure if this sum to 1. Maybe I'll find it out later.
Okay. Okay.
Yeah.
Just wait like a checkout or
Yeah, I mean, if you take the max of each of the columns and divide, then you may normalize them. So you can say in some sense that normalized centrality. This
Mhm.
could be another way.
Okay.
Yeah.
Just a general question.
Okay. Yeah, next we can go to community detection. It's a very interesting topic to see, like given a graphs, if you can, if and most of the times there are no labels associated, so you can think of this as like more uh, unsupervised learning. We are just based on just connectivity or trying to find some patterns inside the graph, and there are like different algorithms for this. And the goal here is to find some communities and clusters. And one example could be like a biological example, which I have worked on, is in terms of like cancer, when you have a tissue lying and then you have different kind of cells. And once, even if you look those cells from a microscope, you may find some tumor cells occurring together. You may find some immune cells together. So that could be one example of a community detection. Or a simple example could be from social networks, that given, let's say, Twitter accounts or X accounts now. So if people are connected with each other, is it like people who follow some sport, do they follow each other as well, or some kind of some phenomena like the no in the node classification example, we looked at like politics or whatever political party they follow. So do they also follow each other? So this kind of analysis is possible just looking at the communities. Yeah, and then there are several algorithms here, and we'll look at each one of them. We'll not go into detail that much, but because they all provide different results, so it's just that it also comes down to like what's the thing you're trying to find. Okay, and let me run this. Okay. Okay, first one, we'll look at the low-vein community detection algorithm. It's very popular. And right now, based on this algorithm, we're trying to find out some communities in our Zachary Karate Club. And before we even go to community detection, just looking at this plot, uh, I can find like 3 communities just by looking. For example, the bigger, like for example, starting with node 0, 21, 17, 12, 3, 7, 1, this whole. Another community is the node 16, 5, 6, 10, 4. And another one is this big community at the bottom of the plot. But now the question arises that can some mathematical algorithm discover this? So that's why we'll look at like 3 algorithms now. And first we'll look at community detection using the low-vein algorithm. And 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 network X is nice because it provides us like functions built in to kind of do this analysis. And so once we run this set, what we are doing is that once we are finding the partition of the communities using this tab 10 color map, we are coloring each one of the nodes. And once we plot it, we can see that it was able to show us some communities. For example, here on the left, we have original Karate Club graph from Zachary, but once we run the community detection algorithm from Lovain, we are able to see that there is like 3 or 4 communities together based on different colors, but you may or may not find them. And it's also possible that these algorithms may not be deterministic. So if you run them again, you might get like a different result. So yeah, okay. Yeah, next One is these two Girvan-Newman algorithm and label propagation. And once we run this, we find out that they also find communities, but it's very different from what we found earlier. So for example, in the Girvan-Newman algorithm, it basically just follows the observation we made that there were initially that there were two communities. In the bottom half there is one community, and in the top one there is one community. But on label propagation, it tells us like a different story, that okay, so it was able to find out that some communities are common, but then here, based on label propagation, nodes 10 and 14 were linked to this community with this hub 0 instead of a different hub. So I guess it's becomes very subjective that which community detection algorithm uh, you want to use, and some algorithms may be better for other cases. Any questions before we move to graph traversals?
I have a quick question here.
Yes.
Does the plotting style change the distance between nodes? And if so, does that change how this algorithm assigns clusters?
I think the algorithm just assigns clusters because there is no concept of like weighted edge in what we are plotting right now. So
Got it.
because each edge has the same weight. There is a version of Zachary Karate Club which has like an edge distributed. So then so there are edge weights in this, and then the community detection algorithm will take care of those edge weights. But this is like a simplistic example where all edges are equal. It's just that we have the same distribution because we have the same position of nodes already, because I am using a seed 0 here. So
Okay.
every time I run this code, it's going to give me the same XY coordinate.
Cool. Thank you.
Yeah, so let's say if I change the seed, let's say 2, and if I plot, then I should be getting like a different orientation of the nodes.
Oh, yeah.
And in here, you might see that some nodes are clustered better. Like for example, if I run the same, so it will give us the same result, but now it's this like the XY coordinate of the nodes have changed.
That makes sense. Thank you for
Yes.
explaining that.
Yeah. Okay. Let's just put back it to 0. Okay. Yeah, and then it's back to what we saw. But see, as I said, it was deterministic because now I ran it again. Initially, these nodes 0, 12, 13 were in the same, but now it's considering this node 16, 5, 6, 10, 4, 0 in a different community. So I think that's the one thing about low-end algorithm. If you don't fix the seed by going inside the algorithm, it's going to give you different communities every time you run it. But that's not the case with label propagation or this Girvan-Newman algorithm. You might get the same communities every time you run. Okay, going to graph traversals. So why we are just like traversing? Because it's useful in multiple applications. For example, detecting shortest path. Let's say you have, or probably like one of the earlier versions of Google Maps, that's how it used to work, is just have like a shortest path algorithm if you want to go from point A to point B. Or if you're crawling website, let's say you're scraping some data, probably like right now, like ChatGPT is popular. So how did they even collect all the data? So probably they ran a web spider which just copied all the data together and put it into one big database. Okay, so there are two different types of graph traversal algorithm. The first one is breadth first search, and the next is depth. And by the name itself, it suggests like a lot of information, that breadth first search, which means that it's going to be wide instead of going into deep. And for example, it just looks at the first level neighbors together. Once it takes care of all the first level, then it goes into the next second or nth level of node in the graph. and for these algorithms to, there has to be a source node, and then only we can define the BFS and DFS. And DFS is popular in using puzzle and maze solving, that you have a puzzle and you start from the start, then how quickly you can go to the end. And given this, and consider like there is some graph and you want to start these traversal algorithms or BFS and DFS. So for how this BFS works, that it will first visit all the first level nodes. For example, if you start at node A, you will visit node A, B, C, and D first. Then you go to the second level, that's E and F. So how the traversal would look like, you go to A, B, C, D, and then E and F. But the DFS, since there is like in the name itself, it's a depth, so it will first go deeper, and then once it reaches like the final nth level, it backtracks to the second level. So for example, in DFS, if we run, it goes from ACE or ADF. It's also possible that it can go from like ACE and then DF and B. So for example, here it runs from ADF and then it goes back to C, and then it starts exploring that part. Once it reaches the end, it goes back to B. And the key distinction is that DFS delves deeper into the graph, prioritizing the exploration of nodes which are farthest as possible before it backtracks. In contrast, BFS, as the name suggests, it takes the wider approach where it first look at all the adjacent nodes and progressively moves to the next level. Okay, and to demonstrate this, we'll start from the same example we had initially, the example of graph G. It should run, yeah, where we have these 6 connections between these 7 nodes, and how you can have BFS here. So right now, I'm not using the BFS defined in the NX, but have our own implementation just to have that. So to run this, what you need is like a implementation of a graph and then the start node. So for example, in this graph, this is graph G, and then you want to start with a node D or A, and then you will traverse in BFS or DFS. So how it works is that you initialize the visited list node. So right now, initially you haven't visited anything. And so you initialize 2 queues. The first one is visited and the queue of all the nodes together. And while your queue is true, then what you do is keep track of all the nodes visited in the first level and then go to the next level. And once you visit them, you put them into the visited node so that you don't go back to the same node again and go to the next node. Okay, and once we run this, so that this is the function call for this function. It says that we are starting from node A and our graph is node G. So if we run, okay, some error. Okay, now it will run. Yeah, so it says that if you start from A, how the BFS traversal would look like. So since it's breadth first search, so you'll visit all the nodes on adjacent. So now start from A, then we visit B, and then C, and then go to the next level D, E, F, G. So that's what we see here, that we start from node A, visit the first level nodes here, and then go to the next level. Same thing goes for our traversal starting from node D. That we start from node D and then visit its first levels. For example, we start from node D, we go to B and then visit A, and then only we go to the third level and further more levels here. Okay, we can also run BFS on the bigger graph we had in Zachary Karate Club. And let's first plot it. It's the same plot again. And let's say we want to run BFS on this graph starting from node 0. So how it will appear is that it will visit all the nodes which are like directly connected to node 0 and then go to the nodes which are away. So for example, our expected result is that node 0 should have node 1, 2, maybe 5, 6, 7, 3, and then at the last, it should have node 26 here. So if we run this, we see that we actually see all the nodes which are closest to 0, which are at the first level of connection there. And then the node which are like 18 and 16 appear at the end here, which are farther away from node 0. And same thing goes for node number 26. Now, if we want to start from this side, we'll see that, okay, so node 33, maybe 14, maybe this 29 appear. And then we should expect node 16 to be at the end because it's the most farthest away node in terms of BFS traversal. So if you run this, we'll see, okay, if you start on 29, 26, we have 29, 20, 33, all the nodes which are directly connected, but we'll see node 16 and 21, which are located farther away, like here and here. So, okay, coming back to DFS, now we will be going deeper into the graph first before backtracking. And we'll use the same graph. We have an implementation of DFS here. And here we have, instead of like a queue, we have a stack. And we have a visited list here. And whenever we visit that node, we put that into this list. And if it's not visited, we just go to its next neighbor and go deeper into the graph. Okay, if we start from in our this graph at node G, graph G and node D. So what we should expect is that first it should go for B, A, C, G, and then trace back again to its second level neighbor E, and then so should go D, B, A, C, G, F, and then go back to E. So that's what is happening here, is that it's starting from D, B, A, C, and then going deeper, and then comes back to its second level of neighbor here. Same thing goes for if we start from A, that it starts with A, go to B, go to D, then E, and then it goes back to node C, which was its first level neighbor here. Okay, to run DFS on Zachary Karate Club, we can have it here, and then here we are running DFS again starting from node 0. So, and now we'll have like longer loops possible. So if we run from 0, it goes to 1, 2, and then it connects to 3, 3, and then 7, and then 12 here. So it's now traversing a loop here, or traversing longer paths until it goes to a node which is at the edge, and it comes back to its next first level neighbor. Yeah. So because like here we can see that although the node 11 is directly connected to node 0, but it in the order of DFS, it appears at the last because it's the only, like one of the only nodes which is like only has one connection and is connected to 0. So that's why it's appearing at the end. Yeah, same thing goes with if you start your DFS from node 26, because in the order of how the node appears in the traversal, node 16 and 11, which are far away from 26, appears at the end. Okay. Any questions till now before we go to shortest paths? Okay, let's talk about shortest path. Like how do you even find shortest path? So to illustrate this, let's create a graph of cities and distance. So right now we have an undirected graph of some hypothetical cities and then some distances, and the source and target. So source node and target node we have defined in a list, and we use the same add edge function here. What it does is that it creates a graph connecting all these cities with different, and we get the edge labels as well. And once we plot this, we should be able to get one such graph where there are several cities, and you can consider like a road map where there are different cities connected with each other through roads, and you have distance on them. So for example, let's say you want to go from Brighton to Blue Whale, then there are so many ways possible to reach Blue Whale. Either you can go from Brighton to Clearwater, then Riverwood, then Portland, so Silverton, then Blue Whale. So there are multiple paths possible. So we would like to know what's the shortest path here. And if you are just ask like if you don't know like any algorithm, the most common answer is that, okay, let's calculate all those paths and then pick the path with the lowest length. That's the brute force way. And then if we can run DFS, so this all simple paths algorithm in network X uses DFS to run. And by running this, what we can do is just see how many unique ways are there to reach from Brighton to Blue Whale. And once we run this, it says, okay, there are like almost 24 ways. And since this is a smaller graph, you can actually calculate all those path length and the paths, that how many ways are there to go from Brighton, starts from Brighton and ends in Blue Whale, and what's their path length. But so once we iterate through all of the paths, we can keep track of like what's the path length here, and then we can pick one with the lowest length. And it works because we have a very small graph, but this thing has an issue that if there are like lots of nodes and lots of edges, then we go into a computational complexity problem that we cannot just take care of the increasing graph size. And again, storing all those paths require a lot of memory. So both computational complexity, like the time and space, both are huge for doing a brute force way. So is there a smart way to do it? And before even go to that, if I ask you that, is there a longer, like the longest path? So hypothetically, since it's like a hypothetical example, we have undirected edges. You can go into like an infinite loop where you keep going to the same cities and never reach Blue Whale. That's like one of the drawbacks of DFS, is that sometimes DFS can get into infinite loops. Okay, and like we discussed, why calculating all part is inefficient, because as the node size or the graph increases, we'll have to store everything into the memory and it will gonna take a lot of time. So we'll look at the shortest path algorithm, which is called a Dijkstra algorithm. And that's how I understand is that imagine, let me zoom out a little bit. Okay, and imagine that you are in a city trying to find your friend's home, and you have a map. So how did Dijkstra work? So you begin at your house and then say that's a starting point. And then there are two things. Either you explore, or if you don't explore, if you explore, you update and then keep doing the same exploration again and again until you reach your friend's path. So from your starting point, you look at like all the streets you can directly travel and note how long each journey would take. So you're not looking very far ahead in terms of the node, you're just looking at the closest neighbors, and whichever is the shortest one, you move there. Okay, now from this new point, you again look at all the places you can reach there, including your friend's house, and keep doing the same thing again and again. You keep repeating this process from a current spot, updating times or let's say distances, moving to your closest location until you reach your friend's house. If you reach your friend's house, that's the shortest travel time or shortest travel distance to your friend's house. Okay, and how this Dijkstra works is that it maintains a priority queue of nodes. So by priority just means that if it's closest, then it will get a higher priority in terms of traversal. And the issue with brute force is that this priority queue based optimization of where you want to go is absent in the brute force approach. It's just in brute force, you're just trying to go to all the nodes and then trying to find out all the paths and then picking one later. But here in Dijkstra, you follow a priority queue approach for the nodes, and that's how you can find out very quickly that what's the shortest path. So once we run this Dijkstra algorithm saying what's the source and target, it actually tells us that it actually matches with the brute force way, that shortest path to grow from the city Brighton to Blue Whale is take this path with this length 315. And here I've provided one function. Let's say you want to visualize. So for example, let's say this is a small graph. So you can see that based on the answer for Dijkstra, it says go to Brighton, Laketon, Riverwood, and then it's suggesting like a very straight path. Just go to Brighton, Laketon, Riverwood, Silverton, Blue Whale. start, and Brighton is the start, Blueville is the end, and then you will have these three nodes in between. But what if you have, let's say, a very complex graph and then you want to see? So I provided a function here where what it does is that it takes this path as an input and then highlights whatever nodes you want to visit. So once I run this, it will tell me that if I want to go from Brighton to Laketon to Riverwood, that should be the path your agent or you should follow from going from Brighton to Blue Whale. Okay. A more complex example would be to simulating landmarks in a city. So let's say you are in a city which has a lot of touristic landmarks, and let's say, for example, here 100 landmarks, and there are multiple ways to reach. So for example, let's create a graph first. This is a random graph with some kind of edges. And let's say you want to go from node number 43 to node number 44 by looking at some of the landmarks. So what should be the shortest way possible? So what you can do is run single source Dijkstra here, and you will get like a set of nodes. And then based on the highlighting function, you can visualize and it will tell you, okay, so if you want to go from node 43 to 44, this should be the path you should take. And then, so you go from node 43 to 60 to 16, 63 and 44, and that should be your shortest path. Okay, some considerations here that it might be, so calculating all paths might be conceptually simple, but it's inefficient because as the graph size increases, you would have like a longer time and space complexity. And so Dijkstra is a good option, but there is an issue with Dijkstra is that it doesn't take care of negative weights, which means that if, so weight distance cannot be negative, but let's say you are trying to do an optimization problem where there is some discount available on some routes. So that would fall under graphs having some negative edges. And for that, you will have this Bellman-Ford algorithm, which takes care of the negative edges problem. So to illustrate Bellman-Ford, we'll just quickly go through this. So again, we'll have a network of cities, but here is that there are negative edges, which means that it's a discounted route. Like if you follow this, your total cost is going to be less. Let's and then let's say you're running like a movers and packers business, and there are some routes which are favorable for you. So then we can represent them as negative edges here. And let's say our New York is source city, and then we have like Tucson also in the network. And once we plot it, so that's how our network looks like. So for example, there is no direct way to go from New York to Tucson. There are multiple paths to go, but what's the optimum path? And there are several paths here which are discounted. So for example, going from Chicago to San Antonio, you have a discounted path which has edge -25, San Antonio to Tucson, which has -20. So maybe if you follow this route, it might be beneficial for you. So Bellman-Ford is actually, it's not like a source to target algorithm, but the most efficient ways to just like so let's say if you want to know, if you want to reach all the cities together, then what's the most efficient ways? So if we call the Bellman-Ford function here from NX, and if we run this, we find that although we saw in the graph that New York to Chicago is 15 units of some hypothetical weight, but actually Bellman-Ford suggests that New York to Chicago will just only cost 5 because there is an alternative path which takes care of the discount we are getting on our path. So for example, Bellman-Ford is suggesting that from going from New York to Chicago, you should actually take this path, New York, Houston, San Antonio, and Chicago, which may have a lower cost than the actual directed edge. So for example, if we follow New York to Houston, it's 20. We can just keep adding things. Then San Antonio, here it's 30. And okay, and then we had this negative edge, which illustrates the discount here, that if you go from San Antonio to Chicago, it might cost you less. So instead of taking a direct path, in some hypothetical situation, you might be better taking this route. to Chicago instead of a direct path here. Okay, and let's try Dijkstra and see, let's say what's the problem is. So it's obvious that Dijkstra will give an error, and it says there are contradictory path found and negative weights. So that's like an inbuilt thing into Dijkstra that it will not work with graphs which have these negative weight problem, or have this characteristic that some of the weights are discounted in terms of like a negative weight. Okay, and let's have this visualization function, and let's say you want to go from New York to Tucson. So there is no direct path possible here. So how do you even go from New York to Tucson here? So then running a graph traversal algorithm can actually find a way. But let's say if this graph is big, this might be troublesome. So then we'll use Bellman-Ford. And once we run the Bellman-Ford saying what's the source and target, we can actually visualize using this function. And it will tell, okay, if you want to really go from New York to Tucson, based on this graph formulation, you should go from New York to Houston to San Antonio, and then you will have a discounted path, which will take you from San Antonio to Tucson in the lowest possible cost. So that's how you can use Bellman-Ford to find out the shortest path if your graph have negative weights. Yep. Yeah. So that's it for today, guys. Thank you.